Stephen, please go ahead and give us your presentation.
So yeah, this is some of the work I did at the end of my PhD, looking at how deposition technique affects charge and excitons in OLEDs. So as we all know, OLEDs are great. They have all these benefits, and they have been successfully commercialized, but there's still opportunity for improvement. So in particular, there's room for improvement in the manufacturing process. So at the moment, the kind of standard process for making high quality small molecule OLED films is vacuum deposition. But solution deposition offers a number of advantages in that we can make larger area devices, get higher yields. But there is the problem that if you make a small molecule device with solution processing techniques, it tends to degrade faster than its vacuum deposited counterpart. So the goal of this work has been to try to understand why that's the case. So I've been looking at how the deposition technique affects charge and exciton dynamics, and whether trapped solvent might have an effect there. And I've been doing that using Kinetic Monte Carlo transport modeling and molecular dynamics structure modeling. So firstly, for the structure modeling, I've been looking at an active layer of OP-ACAC in CDP. The reason I've chosen this blend is mainly because of available data, which I'll get to in a second. But just something to note for future is if we look at the energy levels, we have OP-ACAC acting as about a 0.4 electron volt trap for holes and a relatively shallow 0.1 EV trap for the electrons. So firstly, for vacuum deposition, that's roughly what the simulation looks like. So we take a graphene substrate and we essentially drop molecules onto it a few at a time. And we choose those molecules in a ratio to give the blend that we want, in this case, about 5 to 8% guessed. So then we can repeat that dropping process in steps up to the film thickness that we want. And once we reach that, just allow it to settle for another 5 nanoseconds, just to make sure everything has relaxed and settled into place. Now, the more interesting process is modeling solution deposition, and Tom Lee gave a nice talk on this at our last in-person seminar for those who were there for that. Yeah, basically, the process that they came up with is to take a 10 nanometer thick vacuum deposited layer, space it out over about 80 nanometers, and then fill the gaps with chloroform as their solvent. Chloroform because it's small, easy to simulate, and they could easily get it to boil off. There are a couple of problems though. The first one being that it's very slow to simulate. So this starting system has millions of atoms in it, and has to be simulated for quite a long time for all of those chloroform molecules to leave. So that's the first limitation. And the second thing is that 10 nanometers is relatively thin for an active layer. So I've had a look at how I can improve those things a little bit. Now, we can do that by taking advantage of some of the properties of these systems. So this is a figure from Tom's slides and paper showing the density profile of the layer. And we can see that as the film dries, it tends to form this skin at the top. Whereas lower down in the layer, it's essentially at the same density as the initial system. And one interesting side note that we'll come back to is that it's plausible that as much as 5 to 8% solvent is trapped in the layer on experimentally relevant timescales, so hours to days. So to start with, that's another problem in trying to get all of that solvent out in our simulations, but also it means that that trapped solvent could possibly have some effect on device performance. So the first thing I did to speed up the simulations is look at deleting some of the molecules. Now, you can't delete molecules too fast or you'll end up with spinoidal decomposition where you get kind of a random phase separation of the two, the solvent and solute, or you can alter that density profile and end up with an incorrect result. So there was a bit of testing and figuring out how fast we can actually delete these molecules. But what we ended up doing was deleting up to 10 at a time in per 40 picosecond step. And we choose targets for deleting that are at least 5 nanometers apart. And we choose them from this zone here, kind of just below the skin. So we detect where the bottom of the skin is based on the atomic density of the solute. And then choose solvent molecules that are below that area. So these are in the area where it's close to the initial solvent to solute ratio, but they're relatively close to the top. So they're likely to eventually escape, but they're not busy holding open a percolation pathway or doing anything else in the area of interest. So we can safely delete some of these without affecting the dynamics. So that's great. We can get kind of a almost twice as fast boil off rate by deleting some of those extra molecules. But the other problem was that we wanted a thicker layer. So a suggestion that Alan Mark came up with was that what if we kind of add in some extra molecules? So as we were saying, down in this bottom section, the density profile is, or the density ratio is about the same as the initial system. So what if whenever the skin gets below a certain point, we split the system out and take some extra molecules from the initial system or something near the initial system and insert them into that gap. And now the time correlation of the trajectories of these molecules is quite short. So the system kind of forgets very quickly about what happened in the past. And it turns out that if you do this, it tends to very quickly forget that these molecules have been inserted and go back to the same sort of density profile. So this was an insertion event, just showing the 40 picoseconds after an insertion, with and without the solvent shown. And here we can see the 40 picoseconds before insertion and 40 picoseconds after. So we can see it's getting pretty close to looking the same. We can do it a bit more rigorously as well by looking at the density profiles. So the blue line here is the density before insertion, shifted up so that the top aligns with the density profile straight afterwards. So then the red line is our density profile immediately after insertion. And we see we do have these kind of little void gaps from where we've made sure molecules aren't overlapping with each other. But then if we run it for just 1 nanosecond, then there's no sign in the density profile that this insertion event has occurred. We do see the peak has come down a bit from more solvent molecules coming off, but essentially the system has forgotten that we've inserted extra molecules. So that means that we can build up a thicker layer without having to start from a huge initial system. So with those MD simulations ready, the next thing is to look at how we do the kinetic Monte Carlo modeling. So a bit of an overview for those who aren't as familiar. Essentially, the way a KMC model works is that we'll have a number of possible events in the system, and every time step we'll choose an event randomly based on its rate, and then increment the time based on the sum of all event rates. And the way this time increment works is such that the more things that could happen, the shorter the time step is, so that the overall dynamics of the system don't change. So as an example, we have here 2 parallel electrodes across our layer with all these arrows representing possible injection events. So we might have an electron injected, which can then hop around in the system or back to the electrode. It might move along. We have a hole come in. As we simulate, we progress through the system. They meet each other and form an exciton. That exciton can then also move around and then decay either radiatively or non-radiatively. And there's other interactions as well that I'll get to. So basically what's included in this model is we have charge injection and hopping back to electrodes. And we've assumed ohmic contacts so that those injection rates are scaled so that we preserve a zero electric field at the electrode. Once the charge is in the system, it can hop between molecular sites within a 3 nanometer radius. And then an electron hopping to the side of a hole or vice versa results in an exciton formation event. And that exciton is randomly assigned as a singlet or triplet in a 1:3 ratio. And then if an exciton hops to the site, or sorry, if an electron hops or hole hops to the site of an exciton or vice versa, then we have exciton polaron quenching. So that exciton will be just removed from the system. So then for excitons, we have singlet transport through host to host and host to guest Forster transfer within a 5 nanometer radius. We then have for singlets on a guest molecule, they can go through intersystem crossing with some rate to become triplets. And then triplet transport, we have guest to guest Forster transfer, also within a 5 nanometer radius. And then guest to guest, guest to host to host, and host to guest Dexter transfer within a 3 nanometer radius. And we can calculate rates for all of these based on site energies and their separation. In this case, I've been using the fairly simple Miller-Abrahams approximation just to keep things relatively easy to do. So then the other thing to worry about is exciton interactions, which is triplet annihilation, singlet annihilation, and singlet triplet annihilation. And all of these were considered if one exciton ends up on the site of another, then one of those excitons was quenched. So some of the limitations that we do need to point out, firstly, is that the molecules are being treated as point sites, and this is done mainly for computational reasons. So delocalization is not accounted for. The orientation of the molecules isn't explicitly included. So we don't have any anisotropic effects coming in there for the transfer rates. And we also assume that the molecules don't move during the KMC simulation. So they're kind of fixed in place. Then some other approximations we need to make. So we've said that hops to or from solvent molecules are not allowed, just because they're very unlikely in the first place. And then we're ignoring the effect of trapped solvent on the site energies and polarizability, since including that is also quite complicated to do. And we've assumed that the site energies are sampled from a Gaussian distribution. Now, one other issue that we had to get around is when we create these molecular dynamics deposited films, we end up with quite a rough top surface. And if we were to put an electrode straight against that, you end up with injection hotspots at kind of the peaks, which will likely, because it's such a thin film, will probably distort some of our results. So what we've done is put some kind of prototypical transport layers around the film. And this is just a cubic lattice that we've fitted to the rough surface. So it kind of fills in the voids. And we've, again, randomly assigned energetic disorder and chosen transport parameters so that electron and hole transport in the transport layer is, well, mobility, is the same. And just to validate this, so we ran a simulation where the ERPI molecules were treated as if they were CDP, just so that any kind of density variance across the film didn't matter. And we can run in forward and reverse bias. So the blue line here, or the solid line here, is forward bias, and the dotted line is reverse bias, but flipped. And we can see that we get the same number profiles of all our species. So these transport layers we put there, the fitting of the transport layer to the rough surface isn't affecting the dynamics of our system. So in the actual simulations, we end up with a 17 by 17 by about 13 nanometer layer MD film for the active layer. And if we repeat that periodically, we get a 50 by 50 nanometer active layer. The reason we go to this size is so that we don't have any finite size effects from electrostatic interactions. And then we add about a 14 nanometer thick transport layer on either side. So then for the vacuum deposited layer, we have 2 molecular dynamics realizations, and each of those with 2 different disorder realizations. And then for the solution deposited layer, we have a fully dried film where all of the solvent has been removed. Most of the solvent at the end of the simulation had to just be deleted because it takes too long to boil out. Then we also have a film with a 1:4 ratio, which corresponds to about 5-8%, the kind of maximum expected experimentally trapped or experimentally relevant amount of trapped solvent. and then one with a 1-to-1 solvent to solute ratio, just to try to pick out any trends in the data, since these two were quite close to each other. Now, because of how slow the solution deposition simulations were, even with the modifications, we're talking months of simulation time, we only have one MD realization for each of these ratios. So for each of those, I have 3 different disorder realizations. So so from there, we run 4 different KMC simulations per disorder realization and kind of average over the steady state properties over quite a long time. And that gives us 12 total data points for each solution deposited film and 16 total data points for the vacuum deposited film. So you'll see in the coming slides, there are some error bars, and those error bars represent the standard deviation of the mean for these data points. But they should come with the asterisk that with more MD realizations, particularly for the solution deposition, there could be some further variance. So to get into some results, firstly, we can look at mobility, and we see that for the whole mobility, we've got the red line and the blue line here that are directly on top of each other. There's essentially no difference in between the vacuum deposited layer and the fully dried solution deposited layer. As we go to more trapped solvent, we get slight decrease in mobility, but it's relatively minor. And we see basically the same thing for the electron mobility, but we do have a bit of a difference between the vacuum and solution deposited layer. So why are we seeing this for electrons but not holes? And if we look at the number of host molecules that an electron or hole visit on average, we see that electrons are visiting quite a large number more host molecules. That's because the trapping depth of the AUCAOS in CDP is relatively low for electrons. So we have this higher percentage of host transport for the electrons. And if we look at the orientation of the CDP molecules, we see that in the solution deposited film, there's kind of a broader distribution of orientations relative to the substrate. And since CDP is a relatively long molecule, if we were taking the center of mass, then we can see we'd have a longer hopping distance for electron transport between CDP molecules. So since electrons are being transported more through the CDP, it seems that this is why we're seeing that difference. And with a more realistic transport model, where anisotropic transfer rates are properly taken into account, there may be some other differences there. Now, all of this orientation data does come with the asterisk that it's before thermal annealing. So we see here that there's quite a small distribution of angles for CDP in the vacuum deposited film, basically showing that they tend to prefer to lie down against the film. But there has been previous results showing that after a thermal annealing step, you get essentially randomly oriented molecules in the bulk. So we can't draw any major conclusions from this. Now, the next thing we can look at is singlet to triplet conversion. So for singlets formed in the host, we can look at the probability that they either reach a guest molecule and go through intersystem crossing, which is this solid line here, or that they're quenched by singlet-singlet annihilation, which is the dotted line. And we see we get very good agreement for all of the different films that we simulated. So essentially, there's no difference in the probability that a singlet becomes a triplet in these different films. Now, singlet triplet annihilation and singlet polaron quenching were also included in the model, but they occurred in very, very low frequencies, so they're not plotted here. So the next thing we can look at is the triplet quenching. And since this is the only exciton polaron interaction, this is quite important. So there's been experimental results previously that suggested that the degradation of solution of these films is due to aggregation of molecules induced by exciton polaron interactions. So we're quite interested in whether there is any difference in triplet polaron quenching. But what we see is that for experimentally plausible concentrations of trapped solvent, there's essentially no difference in the probability that a triplet undergoes triplet polymer quenching. Now, the important thing here is this is saying that there's essentially there's no difference in dynamics as far as we can tell. So the fact that we do see faster degradation in solution deposited films suggests that that degradation, or the degradation process, is faster in those films because of the differences in morphology directly, not because of differences in the charge and exciton dynamics. So just to summarize, firstly, we've seen that layer insertion is quite a convenient way to build up a thicker solution deposited film without a prohibitively large initial system. We've also seen that we can get some minor, or we do see some minor differences in some of the transport dynamics, but nothing major. So overall, we get very similar results, at least within the limitations of the transport model used here. And that does agree with some experimental results that show that before degradation, you do get very, very similar performance in these blends. And the similarity of exciton and polar interactions suggests that the faster degradation that we do see in real devices is likely a direct product of the morphology of the film. So possibly the trapped solvent is allowing those molecules to move a bit more freely, or something else is going on there. But it's not, or it doesn't appear to be directly related to differences in charge and exciton dynamics. So for future work, it'd be good to look at using some higher accuracy event rates that can properly take into account molecular orientation and the effects of trapped solvent on site energies, since trapped solvent might make a site more or less of a trap in the local area. And it'd be also good to directly model the degradation process and see how trapped solvent molecules in the vicinity affect the speed of that process. So I'd like to finish by thanking my advisors from PhD, so Professor Ron White, Dr. Bronson Philippa, Professor Paul Byrne, and Professor Alan Mark. I'd also like to thank Dr. George Van Vuunis for his input, and Dr. Martin Strohert and Audrey Sanzoni for their help in getting the MD simulations up and running. Thank you.
Thank you very much, Stephen. So we'll open up to questions. We have only a little bit of time, but just very quickly, if anyone has any questions, please feel free, unmute your microphone and go ahead.
All right. Yeah, I've got a question. I don't know if my microphone's working.
Yes.
Yep.
Yeah, so I think slide 15, and you're talking about the exciton and like the singlet and triplet transport. You've got your triplet simulations, and you're talking about using FRET as well as the Forster mechanism for your triplet transports.
Yes.
So two questions: why would you include FRET for triplets, which should be entirely Forster driven? Sorry, Dexter driven. Yeah. And also your distances for the distance for Dexter transport, like 3 nanometers or something other like that, seems like you could probably cut that down significantly. I would have thought at 3 nanometers, your rates would be essentially 0. You could probably not even bother calculating that sort of stuff. Is that?
Okay, so firstly, FRET for triplets. For guest to guest, where you have these phosphorescent emitters, there have been measurements of FRET rates.
Right.
So I've taken the rates directly from literature there. They are relatively lower than Dexter transport, but it is there. So there's a kind of small fraction of FRET relative to Dexter. And the 3 nanometers, most of the hops are a lot less than that. But I wanted to make sure that I had a large enough radius that I'm not kind of losing any hops that might be kind of going across where a solvent molecule was, or that sort of thing. It's all an approximation, but trying to minimize things where I can. And in terms of computation efficiency, this wasn't a major concern. Most of the kind of slowdown comes into things like handling electrostatics.
Right. Okay. No, that makes sense. Yeah. Just wondering, like, if that's an optimization you might be able to make.
Yeah. Thanks.
All right. I think we will have to stop there in the interest of time. So I'm sure everyone would join me in thanking Stephen one more time for an interesting presentation.